one maximal ideal, and for any lambda which is not in R, then 1 over lambda is this is what is called a valuation ring. Of course, the interest is like in the case of Mark, 1k, big K is the field of rational functions of an algebraic variety over small k.
The second condition implies the first.
Of course. But no important. The maximal ideal is important because you are going to see. You are going to see because the maximal ideal is important. So what do you do with a valuation ring?
An example?
What?
An example for R?
Okay. There are many examples. So I'm just going to take 2 examples and following the philosophy of Ledouin. It is just one example. Okay. So let us do anyway a relation equivalence in K star, which is K theory. So let us say that 2 elements are equivalent if and only the quotient is a unit in the valuation ring. So you can take the quotient and it is an additive group which is ordered. Below is this one. The sum is the product. And the positive part are the elements such that lambda is the maximal area. So this is an exercise for you to show that this is like that. And what is called the associated valuation is just the canonical map. And it satisfies 1, 2, and 3 of Marx Spivakowski. So I would like to speak about the center of valuation. Maybe I have no time. You have the notes there, and the proofs are in the notes, maybe absolutely wrong, but you you can try to follow, and I'm sure that Mark is going to speak about that. And so I will be faster in this part of the Center of Evaluation, but I am very happy to have written down the proofs, because it's the first time I have understand. So, the center is a geometrical property. So it is like the identity tangents. So assume that you have an algebraic variety in the complex case. So very easy in the complex case, which is also a irreducible algebraic variety. And consider big K, which is called the rational functions. The rational functions of the algebraic variety. So what is the center of evaluation? So y, a subset of M, which is a closed I take an irreducible sub-variety of M. Of course, it can be singular, and M also here can be singular, but for me, M is never singular, it is the empty space, but it's not important. So this is called center of the evaluation given by R, if and only if, by definition, you have that the local ring along Y is contained in R, and the maximal ideal of this local ring is equals to the intersection of this ring. Okay. So what is the local ring along a sub variety? The sub variety Y may be a point, just a point. So what is the local ring?
You mean MR? You mean
Ah,
the
excuse me,
maximal
the
ideal?
maximal ideal. MR. So the maximal ideal is coherent with the maximal ideal of the evaluation ring. So what is the local ring? So the local ring is just the genus of functions defined generically at Y. And so it is not something difficult. You take the rational functions over M such that Y is not contained in the poles of phi. This means that Y defines a true function at almost all the points. Excuse me, phi defines a true function at almost all the points of Y. This is the local ring. So this is a very, very formal definition, but it means many things. The first statement, of course, is that for any projective variety such that bit k is the field of rational functions, there is one and only one center. This is the thing I am not going to do, because if I do that, I don't do the other things. Okay. And I'm sure, maybe sure, that Mark is going to do something like that. So for any n such that k equals to the field of rational functions n, a good statement in mathematics must be like that. So assume just for a moment, it's not true?
You must ask that M is complete or compact or something.
No, projective.
Ah, sorry, projective.
I have said that.
Yes, sorry.
Here, etc.
Yes, sorry.
Here. So, the condition k equals, the field of rational functions equals to a fixed field is exactly what means the word birational said by Mark. Birational is the change of ambient space given by a blow up. So if you blow up a point and you obtain a new ambient space and maybe an exceptional divisor, here you have M, here you have M tilde. Assume for a moment that you have a valuation which is very special, such that all the centers are zero-dimensional. What is doing the valuation? The valuation chooses a point at M tilde. Chooses. Assume now that you blow up the new ambient space at the point P1. Another blow up. Now the blow-ups are going to be called pi because we are more or less algebraic. What is saying to us the evaluation? That it chooses a new point in the new ambient space. So maybe we can say that the evaluation has I take a tangent. It's not so true because people is going to say to me that maybe the centers are not of dimension zero. But don't say it, please. Now let's do now a little bit of classical analysis. Things which were very difficult when I was young to know when two infinite are equivalent. Two functions, real functions of one variable. We know if one goes to infinity, one goes to infinity, one goes to zero, the other one goes to zero. What's about the quotient? What is a Hardy field? So let us consider the set of real functions of one real variable that are C infinity. But also, let us consider the germ at infinity of that function. So, what is a germ? A germ is just to say that F and G belongs to the same germ F if and only there is, say that F is defined from B and G is defined from C. So take A bigger than B and C such that F restricted to A plus infinity equals to G restricted to A plus infinity. To take the equivalence relation of this, and this is a germ. A representative of the germ is just a C infinity function from one interval, like that, to R. Note that since the functions are C infinity, if we have one element of R, we can do the derivative. What is the definition of a Hardy field? A Hardy field is just a subfield of this set. Containing the constants, if you want. The constant functions are there. So, H must be a field, and also having this property, closure under derivation. Since I'm not going to speak in a very deep way about valuations, this history of the derivation is not so important. But maybe Max Piwakowski is going to speak to you about what is called the Archimedean rank of evaluation. So the Archimedean rank of evaluation is very related with the logarithmic cosines of the derivatives, the logarithmic derivatives of the function. Okay. So how many things can we do? These are the objects of the analysis. Hardy field. Sum, product, and one very important thing. If F is not zero, then 1 over F belongs to the Hardy field. But in fact, if you take the picture, there is something that cannot happen with F. F cannot do that like that. Blue, 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 blue. So the elements of a Hardy field are non-oscillatory, non-oscillating with respect to the zero, but also with respect to anything, because we can do like that, and also with respect to another element, because we can do like that. So if you take two functions in the Hardy field, you can order them. You can say if one function is positive or negative. So it is an ordered field, a Hardy field. More than that, each element of a Hardy field has a limit. Why? Take the possible limits here. Plus infinity, minus infinity, 0. Different from 0. So if you take an element, it's not oscillating, so either it is bigger than C, either it is smaller than C. So you go with the properties of the real numbers to the limit of each element of a Hardy field. So there is the limit, and it is either plus infinity, minus infinity, either 0 or either a non-zero constant. What we are doing with this? Of course, a valuation ring. So, what is our valuation ring? Let us consider as a valuation ring people that has non-zero value. And so non-zero value means you don't go to infinity. Non-negative value. Non-negative value means that you go to 0 or to a constant. So this is a subring of K. And of course, if limit of f is 0, limit of 1 over f is plus or minus infinity. So this is the property of the valuation ring and the contrary. So each Hardy field has inside a natural valuation ring. So if it has inside a natural valuation ring, there is a valuation. So classically, in analysis theory, you say that two functions are equivalent when the quotient of the functions goes to a non-zero, non-infinity limit. This corresponds to say that the valuation of this equals to 0. This is the equivalent to say that so each Hardy field has a valuation, very natural valuation. Okay, now let's go to the geometry and to the dynamical systems. The limit is a constant which is not 0 and not infinite. So you say that to say that the value is 0 is equivalent to say the other things. The valuation ring and not in the maximal ideal. Okay?
Excuse me. What is the geometric meaning of valuation?
The
in geometric points valuation is
why the word valuation? But I don't know because Mark is going to speak in a very historical way. But the usual valuations are the order of the zeros, for instance. The order of the zeros is a very classical way of thinking of a valuation in a geometrical way. More than that, there is a statement of Kaplansky that says that any valuation can be looked as this. But this is another history.
Thanks.
So let's return to non-oscillating trajectories. So maybe you are tired. We can take a margarita now. We work too much here. Do you remember from a former talk what is a non-oscillating trajectory? I remember. It is a trajectory such that does not cut any surfaces. If you have memory, you say no, it's not like that. So I'm going to consider non-oscillating transcendental trajectories. So this means that for any surface, S intersection gamma is the empty surface. So we avoid the possibility that the trajectory is inside the surface. Why that? Because it's not enough transcendental for us. So surface is smaller dimension, you can work in smaller dimension, etc. So let's consider that kind of trajectory. So we have the you remember the Halley fields, the analysis, and it gives to you a natural valuation, and this gives to you a bridge between analysis and algebra, and now a bridge between dynamical systems and analysis, and then algebra, everything done with features. So take the field of original functions of R3. Take your trajectory, and we can do a mapping like that. This is the H. H is the gems of C-infinity functions. Like that. So here you have two polynomials. An element, a classical element, is like that. So we go to like that. Gamma is naturally parameterized, and since gamma is not inside Q equal to 0, so the denominator is not 0. And it is enough to do the application. And the mapping is injective. And the image is a field. And it is a differential field because gamma is an integral curve, the vector field. So the image is a Hardy field. And this Hardy field is absolutely isomorphic today. And there is a valuation, which is the valuation of the Hardy field. And there is a center of the valuation, which is the origin, because the trajectory goes to the origin and this gives positive values to the coordinates. So the center of the valuation is the origin. And also there is another thing. You know that we should grow up the space changes beyond the space. But not the field, not the field of rational functions. Since the grow up is a birational operation. So the valuation is also defined. No, it's also not, it's still defined in K. And there is a center of evaluation in the new projective model of our ambient space. And what is the center of evaluation in the new projective model in the new ambient space? Just a point, which naturally is the tangent of gamma. And so on. So the iterated tangents of gamma.
What did you use
What?
What did you use?
To see that Q of gamma dt is never zero. So now a non-oscillating trajectory gives in a natural way a valuation, and the centers of this valuation are exactly the iterated tangents of gamma. Well, this is maybe preachy, but we have to do something with that. So in 5 minutes, I'm going to tell a little bit of the things I would like to do in next talks with this kind of ideas. First thing, we would like to know the dynamics. And in order to know the dynamics, for instance, we can say that oscillating things are too difficult, assume that things are not oscillating, so we would like to control the dynamics around non-oscillating gamma. For instance, we would like to know what about all the gammas that share the iterated tangents with gamma. This is what is called Galois I don't know what is in the next. So imagine you try to organize all the dynamics around the gammas, at least for the gammas which are non-oscillating. The first thing you ask yourself is if this is enough to understand the dynamics. Maybe there are infinitely many things, infinitely many phenomena, and you are doing more or less nothing. So there is an argument to say that maybe we are doing enough. And this argument is the compactness of the Zariski-Riemann surface. So the Zariski-Riemann surface of a field is just the set of collision rings. Okay. And this is a compact topological space. How can you see that this is a compact topological space? So you do like that. You consider -1, 0, +1 with the discrete topology. Discrete topology. And you take the infinite product of them. The product of compact topological spaces by Cano's theorem is compact. And now you do a mapping here like that. If you have a valuation ring, you take a tab from K star to -1, 0, 1, such that for any phi you take -1 if phi is not in R, 0 is phi belongs to R minus the maximal ideal, and 1 if phi belongs to the maximal ideal. It is not difficult to show that this is injective. And the image, what is the image? So the image corresponds to the things that comes from the fact that R is a valuation ring. But for R to be a valuation ring, is to be a ring, and to be a valuation ring. And if you explain this for each element of big K, you get an infinite intersection of closed sets. So the image is isomorphic to this space, and it is a compact space. So you have one valuation. You can imagine that around this valuation you know things, for instance by reduction of singularities. And thanks to this compactness, a finite number of variations will be enough. So we have also this in mind, even if we are doing dynamical systems. So to end, the only thing I would like to say next days is like an example. To show that next case. There are two types of Galois packages. Why Galois? Galois theory, la teoría de Galois. Galois theory is the theory of ambiguity. So, in the sense that you cannot say that a root of a polynomial is better than another one. And if you touch a root of a polynomial, you destroy your coefficients, your constant, your ground field. You are enlarging the ground field because you have the right of touching something which is forbidden. So what is forbidden in dynamical systems? What is forbidden, in fact, is to take initial conditions. So when you have one trajectory and many trajectories that have the same iterated tangents at this trajectory, if you have to choose one of them, you cannot do algebraic operations. You need to do one thing which is forbidden. You need to say, I am starting here. And this is like touch a root or touching a root of a polynomial. This is why I call this Gauss packages. One is dancing. And the other one is separate. What means a dancing Gauss package? I'm going to end immediately. Now I have a point. I have a curve. And in fact, this curve is not analytic. You have not this axis of spiraling, because the axis of spiraling are not so much transcendental. And anyway, there is the possibility that if you take another curve, they are turning one around the other one, like a dance. And in fact, in the case of dancing packages, what we find here is a formal curve, which is not convergent, that guides the iterated tangents. So when you have dancing packages, each two curves turn around one to the other one. Also, there is an axis, but it's a formal axis of spiraling, and also they cover a big part of the space. Which is a semi-analytic set, open set. And what is a separated package? A separated package means the following thing. If you have one curve of the package and another curve of the package, there is one projection. In fact, it is a sub-analytic projection. One plane projection that separates the curves. This is not possible in the other case because they cut one to the other. If you want, this can be linked with all minimal theory. This is logic, but I think that this is too much for me. So I recommend you to read this book. I'm inside, of course. And in this book, many of the things I have said are proved in the title. And I'm doing a mixture between my things of Fernando, and other things. So in the next days, I will prove that packages are 1 or 2. Okay, thank you very much.
Questions?
Could you write the name of the book?
It's in English, it is very difficult. It is lecture notes, this means like that. All minimal structures. So this means that if you do logical operations, you get always finitely many parts. And real analytic geometry, more or less what we have done. From Fields Institute.
Okay, are there other questions? So if not, we can thank Felipe again.